is Dr. D. Govardhan, Professor and Editor, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is shear force and bend moment diagrams for simple supported beam subjected to uniformly distributed load and gradually varying load. Here the simple supported beam is it is a beam which is supported freely on two supports at its ends as shown in figure. Generally it carries point loads, uniformly distributed load or gradually varying load, or it may be the combination of any one of these two now. That is a combination of point loads or uniformly distributed load, or combination of uniformly distributed load and gradually varying load, or the point load and gradually varying load. Okay, for all the problems, since it is freely suspended at its ends by the knife edge supports or ball supports, hence the movements at this point at A and B is treated as 0 only. And since the body is in equilibrium condition, by using that fundamentals, it is required to determine the reactions at A and B, that is at the supports as shown in figure, for drawing shear force and bending moment diagrams. Here in this problem, consider simple supported beam of length L carrying uniformly distributed load of W per unit length as shown in figure 15. Since the load is uniformly distributed over the entire length of the beam, hence the reactions at the supports both are equal, that is RA is equal to RB, which is also equal to 0.5 W into L, where W is the load per unit length and L is the length of the beam now. Here now consider the sections at a distance of x from A. Here now we have to consider what is the shear force at that section now. Now according to the conventions now, with respect to the given section, that is axis, toward the right side, the forces which are acting upward directions are treated as a negative shear force and downward forces are treated as a positive force. For example, for the given sections AC as well as the BC, with respect to the x-axis now, here toward the right side, that is the reactions at B is acting upward directions, hence it is treated as a negative force. And the load is there which is acting over the beam now, that is acting downward direction, so that shear force is treated as a positive now. But the shear force at any section is treated as an algebraic sum of the unbalanced vertical forces or the shear force which is acting on it now. Now, when we are considering a section at a distance of x from A as shown in figure, which is represented as xx now, the shear force at this section is equal to, since the force at A is acting upward direction, is treated as a positive toward the left side, because and the downward forces are treated as a negative now. So the total shear force is equal to the algebraic sum we have to determine, which is equal to R is the positive minus W into X now, because where W is representing the load per unit length, but we are considering a length X, hence the total load is equal to W into X. It is acting downward directions negative, RA is the positive now, hence it is equal to 0.5 WL minus WX now. The shear force at A, that means where X is equal to 0, that means which is equal to FA, we are calling, it is equal to 0.5 W into L now. Similarly, when X is equal to L now, that is the shear force at B is equal to FB 0.5 WL minus W into L, which is equal to minus of 0.5 WL now. So where C, that means center of the beam, that is X is equal to L by 2. So FC is equal to, that is shear force at C is equal to FC, which is equal to 0.5 W into L minus Wx. But X is equal to L by 2, and substituting we got it is equal to 0 now. That means the shear force at the center of the beam, when it is subjected to the uniformly distributed entire its length, it is equal to 0 now. Since the shear force is increasing or decreasing with respect to the distance from the free ends, hence all the points should be joined by using the straight lines, or in other words, should follow the straight line law. The bending moment at any section at a distance of x is given by from A. Here we are considering here now at this point. It is the moments, the algebraic sum of the moments created by the forces which are acting toward the left side or right side of the section. Here the moments created by the RA, here which tends to bend the beam in the form of U shape, that is having sagging effect, it is treated as positive. Hence the moment created by RA is the positive, and the remaining load which is acting between A and X, it is acting downward directions, having sagging effect, that is treated as negative. So the net result, the net bending moment is the algebraic sum of the moments created by the reactions as well as the load which is acting on it, which is equal to, that is at a distance of x is equal to mx is equal to RAX is the positive minus total load is equal to how much it is here now, W into X, because W is the load per unit length, distance is taking here X now. Total load is equal to W into X, but it is it is acting at the mid of A and X position, that is at X by 2 now. Hence the moment is equal to force into distance required, RA into X minus of W into X into X by 2 now. So which is equal to here now, RA is equal to WL by 2 into X minus half WX square by 2, which is represented in equation number 2 now. So from this equation, it is evident that the bending moment is always proportional to the square of the distance. Hence, the path followed by the curve is treated as a parabolic now. Now, the bending moment at x is equal to 0. That means on substituting x is equal to 0, we got MA is equal to 0 from equation number 2 now. Similarly, where x is equal to L now, that is the bending moment at B is equal to MB. On substituting x is equal to L now, we got WL divided by 2 into x is equal to again L now, minus of W into L by 2 whole square divided by 2, and substitute the values, we got it is equal to 0 values now. Similarly, when x is equal to L by 2, that is the center of the beam, and substituting x is equal to L by 2, we got MC is equal to WL by 2 into L by 2 minus of W by L by 2 whole square divided by 2. From this equation, we got WL square by 8 now. So after getting all these values now, draw the shear force and the bending moment diagrams. From this one, it is evident that the bending moment is 0 at A and B, and having maximum values at the middle, where the shear force is changing its sign positive to negative or negative to positive, vice versa now. Okay, the procedure for drawing shear force and bending moment diagram is, first of all, draw the beam according to the required scale now. Here, draw the line and represent it uniformly distributed over its length as shown in figure now. After that, draw the vertical line passing through the points here 1 and 2 now. Now, at your convenient distance, draw the lines which is represented the length of the beam now. The shear force at a point B is equal to WL by 2, and moreover it is acting upward directions toward the right side, that is treated as the here negative. So negative according to the scales just represent this force both in magnitude and directions. Similarly, draw again vertical and upward directions. The reactions at A, that is the positive. Again, join these 2 points by the straight lines here now. It is known as line like this. Here it is crossing the axis at C position. That is here midpoint of the section now, where the shear force is equal to 0 now. Now, in order to draw the bending moment diagram now, again draw the lines. Since the bending moment, the effect of bending moment, it is bend the beam in the form of sagging, or that is the center of curvature is in the form of concavity at the top, hence it is a positive. The bending moment at the end A is equal to 0, at the end B is equal to 0, and in the middle it is having WL square by 8, just to indicate the according to the dimensions. Now, join these 3 points by using here now parabolic curve. This is known as the bending moment diagram when the beam is subjected to the uniformly distributed load. Now, based on simple uniformly distributed load, we are taking one problem. A simple supported beam 5 meters long is loaded with uniformly distributed load of 10 kilonewton per meter over a length of 2 meters as shown in figure 18 now. So, the figure is given now here. The length of the beam is equal to here now given 5 meters long. It is given here 2 meters from one end. Here is the point D there now, and 1 meter at from A. The remaining 2 meters is having uniformly distributed load as shown in the figure now. Now, draw the shear force and the bending moment diagram for this beam. So, for this problem, first of all, it is required to determine the reactions at A and B now. Since the beam is in equilibrium position now, that means the sum of the vertical forces which are acting on the beam should be equal to 0. The second one is the moments created by these forces at any point on the beam should be equal to 0 now. So, by using these 2 equations, determine the values of RA and RB now. So, first condition is the sum of the vertical forces. The resultant of vertical forces should be equal to 0. Or in other words, the sum of the forces which are acting upward direction should be equal to the sum of the forces acting in downward directions now. So, from this relation, RA and RB are acting upward directions now here. So, RA plus RB is equal to the total load which is acting above it is given now. 10 kilonewton meter is given, it is acting and length of 2 meters now. Hence, the total load which is acting over the beam is equal to 2 into 10, which is equal to 20 kilonewton is given now. Hence, RA plus RB is equal to 10 into 2, which is equal to 20 kilonewtons now. Now, taking the moments about a point A and equating the same to the 0, because according to the equilibrium, the moments created by all the forces at any point on the beam should be equal to 0. Hence, by using the relations now, when I am taking the reference point is here A, how many forces are acting? One is RB, it is acting upward directions now, the weight is acting downward directions. While taking the moments, the forces which are tends to rotate the body in the counterclockwise direction are treated as positive, and the clockwise direction is treated as a negative now. According to the relations now, RB into 5 is equal to here now positive minus 10 into 20 it is there now. This is the force acting now. Total force is equal to 10 into 20, but it is acting in the middle now. Middle means nothing but 1 meter plus 2 by 2 now. That is here it is equal to 10 into 2. Here 1 plus 2 by 2 is equal to 2 now. That is a 10 into 2 total load multiplied by the 2, which is equal to 0. From this relationship we got RB is equal to 40 by 5, it is equal to 88 kilonewtons. RA is equal to 12 kilonewtons now. Now draw the shear force diagram now. So after drawing the just beam according to some suitable scale, draw the vertical line passing through the points. Here A, one more is B, one more is here D point, and one more point just passing through the C point as shown in figure. Now at your convenient distance now, draw the horizontal lines to represent the length of the beam. Here given now, RB is equal to, we got it now, minus 8 now, because it is acting downward directions now. Here 8 is given, and at RA it is a positive, just 12 is given now. Now just represent. Now we required shear force at a point C now. Since there is no force is acting between A and C, hence the shear force at C is equal to RA. RA is equal to, already we determined its value is equal to 12 kilonewtons. Hence FC is equal to 12 kilonewtons. Draw the 12 kilometer already there, horizontal line as shown in figure now. Similarly, at D, if you take now, the shear force at A is equal to, at B is equal to 8 kilonewtons. But there is no force is acting between B and D now. Hence it is a here horizontal now. Between B and D, there is a uniformly distributed load is acting. Because of this one, its value is changing from positive to negative or negative to positive, vice versa as shown in figure now. So you have to join these points by using the straight line, because this value is following straight line law as shown in figure now, because it depends upon the x values now. So this diagram is known as the shear force diagram. Now the bending moment diagram, the convenient distance to draw the lines to represent the length of the beam. The bending moment at B is equal to here 0. At A is also equal to 0. This is required. This is bending moment at a point to C required now. The bending moment at C is equal to RA into AC. RA is equal to 12 into 1 meter it is there. Hence it is equal to 12 kilonewtons. It depends upon the distance when it is more values increasing. Hence join these points by using the straight lines now. That is MC is equal to 12 kilonewton meter now. Similarly, the bending moment at a point to D again, it is equal to, between B and D there is no force is acting now. The bending moment is the product of force and distance. That means when the distance increases, the bending moment values also increases now. Or in other words, is the following straight line law. So the bending moment at D is equal to, we can take it from the left, right hand side forces. That is RB into the distance is given here BD, which is equal to 2 meters now. That is, it is equal to 8 into 2, which is equal to 16 kilonewtons now. Here it is given 12 values now. Now between these two required now, the remaining. Here, according to the problems, first of all, we have to determine the point at which the shear force is becoming 0 now. So, here, the bending moment values is maximum, where the shear force is becoming 0, or it's changing its sign of positive to negative or negative to positive as shown in figure now. Here let M be the point at which the shear force is changing now. So first of all, it is required to determine the position of M now. Assume here the distance between CD is given 2 meters now. Hence, here I am taking now the distance between C and M is equal to X values. The remaining values is equal to here 2 minus X now. This vertical height is representing here now 12 kilonewtons. This vertical height here it is required now. It is representing 8 now. These two are similar triangles now. So by using the fundamentals of similar triangles, it is required to determine the values of X now. That is X by 12 is equal to, we can write it now, that is 2 minus X divided by 8 now. From this fundamentals determine the values of X now. Here 4 3 ja 4 2 is required. From this relation 2 into X is equal to 3 2 ja 6 minus 3X, or we can take it as X is equal to, that is here minus 2X plus 3X it is equal to 6, or X is equal to, okay, here X 2 into X is positive. Here 3 2 is 6 minus 3. When it is coming now 2x plus 3x 5x now. 5x is nothing but equal to, it becomes 6, or x is equal to 6 by 5, which is equal to 1.2 meters now. Here first of all determine the position of, here we required to determine the values of bending moment now. So the bending moment at M is required now. Here we got X is equal to 1.2 meters now. The bending moment at X is equal to, from this relationship we got it now. Here now, the bending moment at this point now. Here at this point nothing but somewhere we have to take this point is here distance is given 1.2 meters now. Now you can consider the forces which are acting toward the left side or right side now. Here I am taking the moments which are acting toward the left side, that the M into X is equal to, we can take it as RB into the reaction force. The total distance is equal to 1 meter plus 1.2. It is a positive because it is having sagging effect now. Minus uniformly distributed load is there. The total load is equal to, here concentrated load is equal to, it is given now 10 kilonewtons per meter, 10. But the distance is only we have to consider 1.2, but it is acting at a distance of 1.2 divided by 2 now. So RB is equal to, already we determined its value is equal to, here now 12. By doing these calculations now, that is 12 into 1 plus 1.2 minus 10 into 1.2 into 1.2 by 2, it is equal to how much it is now? 19.2 kilonewtons meters now. So here 1.2 kilonewtons per meter you have to represent here now. Join these 3 points is by using parabolic curve now, because the moment is proportional to the square of the distance now. Second problem, a simple supported beam 7 meters long is loaded with a uniformly distributed load as shown in figure. Draw the shear force and bending moment diagrams for the beam, indicating the value of maximum bending moment. So the given that in the problem is the length of the span is equal to 7 meters. Uniformly distributed load W1 is equal to, because here now in the figure 2 types of uniformly distributed load that are acting. One is between A and C, the second one is between B and D now. Between A and C, assume this is the W1, it is acting Newton per meter. For a length of 3 meters, it is acting between A and C as shown in figure now. Similarly, in the length of the beam DB, it is having 2 meters length, but this over it 5 kilonewton per meter uniformly distributed load is acting for length of 2 meters now. Now, for the drawing shear force and bending moment diagrams, it is required to determine the values of RE and RB. Here, according to the equilibrium principle, the sum of the forces which are acting upward direction should be equal to the sum of the forces acting downward directions. Here, the downward forces means uniformly distributed load between A and C as well as the B and D. Upward forces is the reactions at B as well as the A now. Or in other words, RA plus RB, which are acting upward direction, should be equal to the 10 into 3 plus 5 into 2 now. So it is equal to 40 kilonewtons. Here represented in equation number 1 now. The second one is the moments created by these forces at any point should be equal to 0 required. So here considering the force, that is moments at a point A, that is sum of the moments at A is equal to, generally it is represented as sigma MA, should be equal to RB is nothing but the force which is acting upward directions, that it tends to rotate the beam in anti-clockwise directions, hence it is treated as positive. So RB into 7, and this load is there now between the B and D. It is acting downward direction, tends to rotate the body in clockwise directions, hence the moments are treated as negative. So which is equal to, total force is equal to 5 into 2, it is equal to 10, but this load is acting in the middle now. So here now from A, total load is equal to 5 into 2, it is acting just 1 meter, here 2 meter means 1 meter. So the distance now becomes only here now 6 meters now. That is we can take it as the moments at A created by the uniformly distributed load BD is equal to 5 into 2 plus total distance from A to the point of applications, that is 1 meter from B there now, it is equal to 6 now. Similarly, for the AC, the total load is equal to 10 into 3 now, 30, but it is acting in the middle 1.5, that is 30 into 1.5 is equal 10 into 3 into 3 by 2 now, that is 1.5. It should be equal to 0. From this relationship we got to RB is equal to 105 by 7, which is equal to 15 kilonewtons. RA is equal to, that the total load should be equal to, already we have taken 40, and so 40 minus 15, it should be equal to 25 kilonewtons now. Now, shear force diagram. First of all, represent the beam as per the suitable scale, as shown in figure here now, and represent the forces which are acting on it. After that, draw the vertical line passing through the points A, B, here A, B, again one more is C, one more is D, as shown in figure now. And at a convenient distance, first of all, draw the horizontal lines for the representation of shear force. Thus, here with respect to the A point, the forces which are acting upward direction are treated as negative forces, downward forces are positive now. Hence, the reactions RA is treated as here now negative force. It should be downward directions. This represents the values 15 downward directions now. And when moving just to B to D now, the downward forces of here 5 to the 10 it is acting now. Here now. Hence, here when you moving nothing but the total resultant force at D is equal to here 15 negative plus 10, that nothing but it is equal to 5 resultant force now. Okay, join these 2 points because this is varying with respect to the straight lines only because of its distance, because it is subjected to the uniformly distributed load, it is varying according to the straight lines now. That means at D, it is having net to 5 kilonewtons force only acting. And between D and C, there is no force acting, hence draw the horizontal lines up to C position now. Now, when I am coming from other end now, that A, the upward forces are treated as positive, hence it is now 25 upward directions. Afterwards, it is a positive. With respect to the C point, nothing but it is acting upward directions, these are downward directions. The downward upward forces are treated as positive, here downward forces are treated negative, hence its value is decreasing now until to meet the given lines, that is at C position. So it is now moving like this now. Here at E position somewhere, just it is crossing the axis of the beam. That means the shear force is becoming here 0 values now. Here at this point it is having maximum bending moment, or in other words, the beam possesses maximum bending moment where the shear forces changes its sign positive to negative or negative to positive, or in other words, its value is becoming 0 now. That is according to the problems, it is the E point now. So this is the shear force diagram now. Now bending moment diagram now. In bending moment diagram, so again it is required the point E now, where it crossing the axis of the beam now. Now these two are similar triangles now. This two, that is A. Here now I am taking now A1, one more point, E, C, C1. That is triangles of A, A1, C, E, C, C1, E, both are similar triangles. Here the distance is equal to, between these 2 points is equal to 3 now. Hence I am taking this in nothing but here now, x distance. This is equal to 3 minus x now. By using trinomial triangles method now, determine the values of x now. That is here now, x divided by 5 is equal to, we can take it as 3 minus x divided by 25 now. From these relations now, 25x is equal to, we can take it as 5 into 3 minus x or 15 minus 5x. From these relations we got 30x is equal to 15 or x is equal to 15 by 30, it is equal to 1 by 2 or it is equal to 0.5 meters. That is from C point, here the maximum bending moment will occur at a distance of 0.5 meters now. Now bending moment diagrams. From the beam, draw the vertical lines from the various points now, like B, here D, one more is C, one more is here now, E point also we have to draw it now, one more is the A point also. Since the bending moment for the simple supported beam is the positive, hence draw the horizontal lines such that sufficient space should be kept above the line AB. Now, the bending moment is 0 at A and B now, because MA is equal to 0 and ME is also equal to 0 now. Just we got these 2 points here now. I require a bending moment at a point C now. Here now. That is, it is the sum of the moments created by the forces toward the left side or right side now. Here I am taking the moments created by the left hand side forces now. One is RA. RA is nothing but having sagging effect, hence the moment is treated as positive now. And uniformly distributed load which is acting downward directions, it is having hogging effect, it is a negative now. So the resultant is equal to sum of these two moments we have to take it. That is, the moment at C is equal to RA into AC. That is, RA is equal to 25, AC is equal to 3 now. That is 25 into 3, take it, minus the total load is equal to 10 into 3 now, 10 kilonewton per meter, 3 meters. The total load is equal to 30, but it is acting in the middle now, that is 1.5 now. Or in other words, it can be written as 10 into 3 into 3 by 2 now. From this relation, we got to 30 kilonewton meter now. So, here now, at this point, we are having 30 kilonewton meter at C position now. Now, one more point is required, just D now. That is, here bending moment at D now. I am taking the moments here now from RA only. Just one side you can take it any side now. When I am taking from RA, that is toward the left side now. The bending moment at D is equal to RA into total distance equal to 3 plus 2, that is equal to 5, positive, minus of The total force is equal to 10 into 3, but it is acting in the middle now. Middle means here 1.5, the remaining is 2 now. That total distance is equal to 3.5 now. Or in other words, is equal to RA into 3 plus 2 minus of 10 into 3 into 3 by 2, that is 1.5 plus 2, which is equal to 20 kilonewton meter. That is here is equal to 20 kilonewton meter. So here now from B, draw a line up to D point MD. Again join here now MC, because just you have to join the points based in parabolic curve now. Here one more point is required, just where it is having maximum values. Already we determined this point is nothing but a distance of 0.5 from C now. So it is required to determine the bending moment at a point E now. So it is equal to RA into, because the 0.5 it is there now, 3 totally, 0.5 when it is removing, it is now becoming 1.5 now. So from this relation we got M is equal to RA into 2.5 positive minus the total load is equal to 10 into distance is equal to 2.5 multiplied by 2.5 by 2, it is equal to 31.25 now. So here represent 31.5. Just join all these points by a smooth curve which is following parabolic curve now. This is known as the bending moment for the beam. We need to subject it to two types of uniformly distributed load. One is between the AC, one more is between BD, as shown in figure. A simply supported beam AB 6 meters long is loaded as shown in figure. Construct the shear force and bending moment diagram for the beam and find the position and the value of maximum bending moment now. Here in this beam, between AC 4 kilonewton meter force is acting now. Again between B and D 2 kilonewton meter also acting now, and between 1.5 from B, that is nothing but in middle of this force, here 5 kilonewton force is acting now. That means it is a combination of uniformly distributed load as well as the pointer now. So the given that in the problem is the length of the span is equal to 6 meters now. The point load at E is equal to, that is 1.5 meters from B, it is equal to 5 kilonewtons. Uniformly distributed between AC, it is given now, it is equal to 4 kilonewton per meter. Uniformly distributed load between DB 2 kilonewton per meter. Now the reactions between RA and the reactions at RA and RB is required just by using equilibrium conditions. So RA plus RB is equal to, that is sum of the vertical forces should be equal to the sum of the downward force, which is equal to 4 into 1.5. Here uniformly distributed load is given, here 4, distance is given 1.5, and here uniformly distributed load it is given 2 kilonewton per meter, but distance is given 3 now. 2 into 3 plus 5, it is equal to 17 kilonewtons. Taking the above moments about a point A and equating the same to the 0, that is RB into 6 is equal to the moments it is equal to, because here now the sum of the moments which are acting in clockwise direction should be equal to the sum of the forces acting in anti-clockwise directions. Hence RB into 6 is equal to 4 into 1.5, but it is acting 1.5 by 2 plus second force 2 into 3, but it is acting 4.5 meters from A plus point is also there now, 5 into 4.5, total it is equal to 54 kilonewton meter. Hence RB is equal to 54 by 6, which is equal to 9 kilonewtons. RA is equal to now becoming from this relations now 8 kilonewtons now. Now the shear force diagram which is shown in the figure now. Here in order to draw the shear force diagram, first of all draw the vertical line passing through point B as well as the here D. One more is the point here now, this E point, here it is, one more is at here C, one more is the A, take it now. This is known as here horizontal lines. The shear force is negative towards the right side because the upward force is at the negative now, right side. And at here now, its value is now from B. Now the shear force at E required now. At E is equal to, shear force at E is equal to 2 minus 2 into 1.5 minus 5, which is equal to minus 6 kilonewtons now. So here take minus 6 now. Just join these points by using the straight lines. After that 5 is there now. It is moving now. From other side, RA is equal to 8 kilonewtons. But here now, when you are moving just toward the point C, downward force is acting. That is the resultant of shear force is decreasing now. From this one, it is equal to now, the 4 is decreasing. 4 into 1.5 means nothing but 6. So, you have to take here 6 now. Just join these points by using the straight lines. There is no shear force changing between these two. Hence, horizontal lines now. After the, because of point load is there, just you have to join now. Here somewhere it is crossing the here axis of the beam, or the shear force is becoming 0, where it is having maximum bending moment now. Okay, bending moment diagram now. Here I am taking the points once again now, all the points now. There, the bending moment at A and B is equal to 0. That is MA is equal to 0 and MB is also equal to 0. Required now. So here it is required now. The bending moment at C is required now. That is the RA into, here it is given 1.5. That is the positive. Minus, here is given, it is equal to MC is equal to here now. Bending moment at a point to C required now. It is equal to 8 into 1.5, that is positive, minus of the total load 4, it is a kilonewton per meter, multiplied by 1.5, total load is equal to, but it is acting in the middle 0.5, which is equal to 7.5 kilonewton meter now. Hence, here represent 7.5 kilometers. Join these 2 points by the parabolic curve now. Now again, the bending moment at D required now. Bending moment at D is equal to, here 8 into the distance between A and D is equal to 3 now. That is acting upward direction, that is sagging effort positive, minus, here the uniformly distributed load is acting downward direction, sagging effort is there now. Total is equal to 4 into 1.5, but it is acting in the middle now, that is 0.7, 5 plus, here the distance between CD is required now, which is equal to 4 into here 1.5 total load, the distance is 2.25, which is equal to 10.5 kilonewton meter now. Hence 10.05 newtons. Just join the points here by using the parabolic curve now. Only we require just M point where it is the crossing X line now. Now I am taking again now the point to here where just E point now. That is where the 5 kilonewton force is acting now. The bending moment at B is equal to 0. The bending moment at E point is equal to, it is equal to RB into, here now RB into 1.5. Here RB into, here given 1.5. It is a negative, but positive force is here now. It is given 2 kilonewton meter into 1.5 into 1.5, 2 now. So from this relationship we got it now 9 into 1.5 minus of 2 into 1.5 into 1.5 by 2, it is equal to 11.25 now. And so 11.25 take it now, just to join the points by using the smooth curve now. So we required here the bending moment at a point M is required now. So the M point can be calculated here by using the similar triangles between these 2 points now. Here now, here one triangle is there, these 2 are there. Here by using the relationship we got it. Here one force vertical now, here two force vertical now. The distance we have to determine now. So the distance between these 2 points is equal to here given now. It is equal to totally 3 meters. It is equal to 1.5 meters now. One is x mean nothing but 1 more is 1.5 x now. So by using the relation now, x by n is equal to 1.5 x divided by 2 now. From this relation, so 2x is equal to 1.5 into minus of x. So by using the relationship, we got x is equal to 0.5 meters now. So the bending moment, here the distance between this point to E to this point is equal to 1.5, 0.5 meters now. So mm is equal to the bending moment at m is equal to, we can take it as here 9 into, when I am taking the forces which are acting toward the right hand side, 9 into total distance is equal to 1.5 plus 0.5. It is having, okay, sagging effect positive. Total load is equal to uniformly distributed load is given 2 into 1 now. And the point load is there 5 there, but it is acting at a distance of 0.5 minus of 5 into 0.5. From this relation, we got 11.5 kilonewton meter. Just to identify kilonewton, just join these 3 points by using parabolic curve. This is known as bending moment diagram for the beam when it is having combination of uniformly distributed load as well as the point load. Now the simple supported beam carrying gradually varying load from 0 at one end to W per unit length at the other now. Consider simple supported beam AB of length L and carrying gradually varying load 0 at one end, that is a B, and W per unit length at the other end as shown in figure 25 here now. This load is nothing but here given W per unit length run now. Now just first of all determine the reactions of RA and RB now. So RA is the reaction set A point to, RB is the reaction set of point to B now. RA plus RB is equal to, that is sum of the vertical forces should be equal to the sum of the forces which are acting downward directions. Here this force is nothing but here now W, here it is 0. Total load is nothing but area under this curve, which is equal to, total load is equal to, I am taking here W, which is equal to, we can take it as W into, here is given L by, here is given 2 now. Because the total area is nothing but area under this curve now, area of the triangle now. Okay, from this relation, it is the equation number and we are taking now. The second one is taking the moments at about a point here now, about a point here at this point, the RB is now moving in clockwise, anti-clockwise directions positive, RB into L, which is equal to now, the total load is equal to W into L by 2, but it is acting, it's a center of gravity. The center of gravity of the triangle is equal to here L by 3 from the base now, that is from end A point. Hence, which is equal to WL by 2 into L by 3, which is equal to WL square by 6 now. So RB is equal to, from this relationship we got WL by 6 now, or we can simply take a W by 3. WL by 2 is the total weight already we determined, and RA is equal to, we got to 2 into W by 3 now. Okay, the shear forces at any section X at a distance of X from B, here assume this will be required at a distance of X here now. Assume at this position now, which is equal to RB is nothing but acting upward directions now. Here we require minus now, that is at a distance of X is equal to, generally we are calling Fx is equal to minus RB, because it is acting upward directions toward the right side, hence negative. This load is a positive now, which is equal to the area under this curve, it is equal to, we required this is nothing but increasing at the rate of W per unit length. Hence, this height is equal to, here it can be taken as W by L into X now. This side. That is, here Fx is equal to Rb. The total load under this curve is equal to, here it is equal to half of, we can take it as W by L into X plus 0, we can take it now. R minus Rb minus of Wx by 2L now. So from these relations now, Rb is equal to, we got to minus of WL by 6. Here it is, it is a plus value acting downward directions plus, which is equal to Wx by 2L now. Now thus the shear force is WL by 6 at B position where X is equal to 0 and increases in the form of parabolic curve because it depends upon the, here the square of the distance now. Square of the distance. Hence, let M be the point at which shear force is equal to 0. That nothing but here it is equal to WL by 6. Here it is nothing but following parabolic curve from these 2 points when it is moving like this now. Here one point it is there now. That's the one where the shear force is becoming 0 now. So that value is calculated by using the relation F is equal to minus of WL by 6 plus W into X square by 2L now. By using the relations now, when Fx is equal to 0 means, by using the relations now, we got to, and substituting the values we got to, that is X is equal to L by root 3, R which is equal to 0.2577 into L now. That is, this is the point where the shear force is becoming 0 now, at which it is having maximum bending moment now. The bending moment at any section X at a distance of X from B now. Here I required, here Mx now. I required Mx is equal to, here this force is nothing but tends to move in sagging effect, having sagging, it is a positive, that is Rb, assume it is X, is a positive, and this force is there, it is acting, total force is equal to, here W by L into X, it is there now, this force is equal to, here it is equal to 0, but we have to take it off, but in moment creating at a distance of X by 3 now. So which is equal to Rbx minus, here now W by L into X square divided by 2 3 is 6 now. This is called just Mx now. When X is equal to 0, the bending moment is equal to 0 at B point. When X is equal to L now, that is the bending moment at A is also equal to 0 now. And when X is equal to, when you are putting 0.577 L, where the shear force is changing its sign, so positive negative, it is having maximum values. So by substituting X is equal to L now, 0.577 L now, the maximum bending moment at this point we got, which is equal to 0.128 into W into L now. So mark this point to join all these points by here the curve. This curve is called here now cubic curve. It is the path followed by the bending moment when the simple supported beam is subjected to gradually varying load now. Here I am taking one problem now. The intensity of loading on simple supported beam of 6 meter span increases gradually from 800 Newton meter run at one end to 2000 Newton meter run at the other end as shown in figure 26 now. Find the position and amount of maximum bending moment. Also draw the shear force and bending moment diagram. The given data in this problem is the length of the span is given 6 meters. The gradually varying load at A is equal to WA. it is given 2000 Newton meter now. At B is equal to given 800 Newton meter. Given. Here this weight is here given now. It is assumed to be split into two forms now. From 8 meters, 8,800 Newton meter, if you draw the lines horizontal parallel to the beam, it is treated as it is a combination of uniformly distributed load and the gradually varying load now. So uniformly distributed load of 800 Newton meter over the entire length of the span is acting, and gradually varying load is varying from 0 at B positions, and other end it is equal to 1200 Newton meter run. It is increasing per unit length now at A now. So the total uniformly distributed load is equal to 800 into it is there now into 6, which is equal to 4800 newtons. Total uniformly distributed load W is equal to, here it is given W is equal to 1200 plus 0 by 2 into 6, which is equal to 4800 newtons. This is the gradually varying load now. So we required the reactions at A and B now. Let RA and RB is representing the reactions at A and B respectively. When the beam is subjected to uniformly distributed load as well as the gradually varying load. Okay, according to the previous fundamentals, we got RB is equal to here 3600 newtons and RA is equal to 4800 newtons now. Now draw the shear force diagram now. So first of all, after representing the simple supported beam subjected to combination of uniformly distributed load and gradually varying load, draw the lines passing through points A and B, and at a convenient distance draw the horizontal lines to represent the length of the beam now. At downward direction it is having here now 3600 newtons. At other end it is equal to 4800 now. Just join here, it is there now. Let M be the point at a distance x from B, where the shear force is equal to, here 0 is required. The shear force at a distance of x from B equal to, it is given by, that is the Fm, which is equal to 0. That Fm is equal to be arriving 3600. It is there now 3600 here plus 800 into x, because of uniformly distributed load we are taking it is at a distance of x now 1600 upward direction. So the downward force is equal to, first of all, uniformly distributed load we are taking, which is equal to 800 into x now. Afterwards it is running at a speed of, it is given now, that is W by L, that is 1200 divided by L is equal to 6 into x, this vertical load, but total load is equal to half, we have to take it now, area, which is 1200 into x divided by 6 into x by 2 now. From this relationship we got to minus 3600 plus 800x plus 100x is equal to 0. From this relationship we got to this x is equal to 3.21 here meters now. So join the points, all these points. So by using the here now parabolic curve, here first one this point up to these positions and these positions. This is known as here now shear force diagram for the beam indeed subjected to both the uniformly distributed load as well as the gradually varying load. Bending moment diagrams. The bending moment at A is equal to 0. Bending moment at B is also equal to 0. Now determine the bending moment at a point M now, where it is changing its sign positive to negative and so on. So here now, the bending moment at A, M is equal to already we got, and B also we got now. It is increased in the form of cubic curve to a maximum at M, where the shear force changes to sign now. The position of M from B is equal to, already we determined its value is equal to 3.21 meter now. the maximum bending moment is equal to here now RB into X minus of 800 into X into X by 2. 800 is a uniformly distributed load. Length we are taking X total load, but it is acting at the middle of X by 2 minus 1200 is given now. It is increasing into X by 6 plus 0 divided by 2 into X by 3. From this relationship we got to 6332 Newton meter. So just to represent these values now, join all these points by cubic curve. This curve is representing the shear force diagram for the beam when it is subjected to the combination of forces, uniformly distributed load and gradually varying load. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.